In this video, I'd like to pick up with where we left off yesterday, and that's to complete this word problem that involves quadratics. And we'll spend some more time talking about quadratics a little bit later in the video as well. Now, our goal was to create a box with a square base and no top, and we're going to do so by cutting the net, we call it, out of a square piece of cardboard. Now, that square piece of cardboard is going to have 4-inch corners cut out of it. When we cut these 4 corners out of the flat piece of cardboard, then when we fold along these edges here, we can end up creating this 3-dimensional shape. Now, the final condition for this particular scenario is that the box itself has to hold 100 cubic inches, and we'd like to know what are the dimensions of the cardboard that are needed. Well, we can start by noting this, that the volume of the box is going to be length times width times height. That's how we find the volume of any rectangular prism. And since the base of this rectangular box is going to be square, then the length and the width have to be the same. So I'm just going to call those W for right now. The height ends up being exactly 4 inches. So if I make those replacements, I might say something like this, that W times 4 represents the height, or in other words, 4W squared represents the volume. I think I said height a minute ago, represents the volume. So the volume of this box, the amount of stuff that this box can hold, is equal to 4 times whatever W, the width of the box, ends up being squared. Now, the width of the box corresponds to these positions on the net, on the flat piece of cardboard that's about to get fitted. And each of these corners that we're cutting out is 4 inches long. So I'm going to ignore those W's for just a second. I'm going to focus on the width of this cardboard. I don't know how wide this cardboard is because we don't know how wide the box itself is going to be. But what we do know is this, that if X represents the total width of the cardboard, if I had X take away 4 and take away 4 again, that's going to leave me with W. Same thing in this other direction. If this width was W and this was 4 as well, then the total length is still X. We're talking about a square piece of cardboard here because this W and that W are the same. W plus 8 would be equal to our X value as well. So I think I may have said that backwards a minute ago, but let me clarify. X is the total width of the piece of cardboard, and that's equal to 4 plus W plus 4. Or in other words, W plus 8 is equal to X. Now our equation over here was built on W, so we need to get W by itself. W by itself would be X minus 8. We've seen that a bunch with our two-step equations that we solved earlier in this class. So now I'm changing W to X minus 8, and I've got volume is equal to 4 times X minus 8 squared. Moreover, our volume ends up being 100. That's our goal. We want to create a box that contains 100 cubic inches. So if I rewrite this equation one more time this way, instead of X minus 8 squared, we can write this as X minus 8 times X minus 8. Now we can distribute and FOIL and see what the right side equation is going to be leaving us with. So I'll leave this 4 alone for a second, and I'll just FOIL this. Multiplication's commutative, so I can go out of order if I want. In the act of foiling, hopefully you've seen enough of these by now to know where this is going. We get X squared minus 16X plus 64 after we combine our like terms. Now if I distribute in, I'm left with 4X squared minus 64X plus 256. And now I see that I've got a quadratic expression on the right side of this equation, and I know that if I can make this equation equal to 0, then I can use the quadratic formula to finish solving. So I'll go ahead and subtract the 100 over to the right-hand side. It combines with this 256, and we're now left with a 4x squared minus 64x plus 156. Now, knowing what we know about our quadratic formula, we can say that our a value is 4, our b value is negative 64, and our c value is 156. We can quickly calculate our d value, our discriminant. That's going to be negative 64 squared, which does come out to be a positive number, minus 4 times 4a times 156. Now, I'm not 100% sure, but I think 64 squared is going to be bigger than this product, so I think my discriminant is going to come out to be a number bigger than 0. But let's check. Okay, so I have this entered into my calculator, and that result comes out to be 1600. So D is 1600. That is indeed larger than 0, so that tells me that we have 2 real number solutions to this quadratic. So the math is going to lead us to believe that there are 2 solutions to this example, but both solutions might not be good in the real world. We'll just have to see what we get. So now that I know that there will be solutions, I feel pretty comfortable going to my quadratic formula program. So QFP and QFM. We'll use an a value of 4, a b value of negative 64, and a c value of 156 in both cases. And since we've programmed our calculators to do this math for us, then we can just enter the expressions as they are to see our 2 solutions. So I had to open the software that I had saved a few minutes ago, and I've done that now. And now, since we've run that, I should say that document, we ran that document, it's got the program built into it. We'll call the QFM program and evaluate that at our ABC values. So 4, negative 64, and 156. And then we'll run the QFP formula. So QFP. This one runs at the same numbers, so 4, negative 64, and 156. And we get a solution there as well. Now these numbers worked out really nice. They're nice whole numbers, and they are both real numbers. So QFM gave me an answer of 3. QFP gave me an answer of 13. Now remember, our goal here was to solve for our unknown variable, which happened to be x. X was the unknown. So this QFP and QFM is saying that x, the width of the cardboard itself, is either 13, or it could be 3, or maybe even both. Well, which one of those makes more sense than the other? Think about what's happening here in the real world. Yes, we have 2 solutions from the quadratic equation, but both of those equations are not good in the real world. Could this could this sheet have been 3 inches wide? That's the claim for one of our solutions. Well, certainly not. This couldn't be 3 inches wide, because if this box or if this sheet of paper was only 3 inches wide, then when we go to try cutting these 4-inch corners out from that paper, they would be too large to fit. However, if the paper dimension was 13, then we'd be okay. 13 take away 4 in 2 of these cases would leave us with a W value, or a width of 5. And it looks like this box would be 5 units by 5 units by 4 units in height. So I'm going to say that the box dimensions have to be, the sheet of cardboard has to be 13 inches square. So the cardboard must be 13 by 13. Now, interestingly, I think we can make a little side note here. The volume, if we end up with a width of 8 times 8 times 4, sorry, that's a mistake. The width of the box ended up being 5 by 5 by 4. That comes out to be 100 cubic inches. And that was necessary. Remember, our goal was to create a box that had 100 cubic inches, and if it is 5 units wide in this direction, 5 units wide in that direction, and 4 units tall, that would produce a box that is indeed 100 cubic inches. Now, to transition into the next point of discussion for this class, having to do with these quadratic functions, is that we know that we're talking about U-shaped graphs, And these U-shaped graphs have a high point and a low point to them, or in other words, a maximum and a minimum value. The quadratic formula that we've been working with have been finding our x-intercepts of these graphs. So in other words, if I know where the x-intercept or x-axis points are that the graph touches, then the U-shape that connects those 2 points could be pointing upside down like this, or it could be pointing right side up like this. The interesting thing about the maximum point or the minimum point for the parabola that goes through those 2 x-intercepts is that that maximum or minimum point is always halfway in between those 2 x-intercepts. So when we're asked to find the maximum or minimum value of a particular function, we could solve and find the 2 x coordinates of our intercepts and then find the middle in between and work from there. So let's see that as an example. In this case, our a value is 1, b value is 1, and c value is equal to 1. So if I go to our quadratic formula calculation, the QFP for 1, 1, 1 should give me 1 x-intercept, and the QFM for 1, 1, 1 should also give us our x-intercept. But you can already tell that we're running into an issue here. The 2 solutions that we've just established with these coordinates end up producing x-intercepts that are imaginary numbers. In other words, there are no real number x-intercepts or in other words, the graph doesn't touch the x-axis. It doesn't physically touch or cross the x-axis. So the graph, I don't exactly know what this is going to look like, but it could potentially do something like this, where it could be a U-shaped graph that opens up like this. It could be a U-shaped graph that opens down like this. But in either case, we never did touch or cross the x-axis. Because of that, that's why we're getting these weird imaginary number solutions. So those 2 graphs still have a high point or a low point. They have a maximum or a minimum value associated with them. So there's got to be another way. Well, there is another way, and it's called using the vertex method. The vertex of a quadratic is the high or low point, or let's go ahead and use the same terminology here, is the maximum or minimum of a quadratic. And the x value of the vertex, we sometimes use this notation here, is equal to the opposite of b divided by 2a. So in this case, if I would like to know the x-coordinate, or the horizontal position of our high point or low point of this graph, all I'll have to do is substitute in a b value of 1 and an a value of 1 as well. And we see that the x-coordinate ends up being -1/2, or -1/2. Now that's all well and good, but we would like to know the actual coordinate. When we say the maximum or minimum value, we really are referencing the y-coordinate, so let's see if we can get that. Well, the y-coordinate of the vertex is simply equal to the function evaluated at the x-coordinate of the vertex. If I take this x value and plug it into the equation, which we know is equal to x squared plus x plus 1, we now have -1/2 for our x values, -1/2. And if we substitute in, we can simplify and find the y-coordinate. So I've got that set up in my calculator, and I'll tap enter here, and the y-coordinate ends up being 3/4. Okay, so it now seems that our vertex, which we sometimes label just v for vertex, ends up being at an x value of -1/2 and a y value of 3/4. Let's go check this out. I'm going to go to Desmos and graph this. There's that equation, y equals x squared plus x plus 1. Change the scaling just a little bit. If I tap on the screen, I can see that the vertex is visible and available to us. And if I click on that vertex point, I see that we have an x value of -0.5 and a y value of 0.75. And if you know anything about decimals, you know that this is -1/2 and +3/4. So that was correct. Now we can use this method for finding a maximum and a minimum in a variety of ways. I'm going to go ahead and stop this video now. I'm going to try to keep this one a little bit short. But I would like for you to try number 34 on your own, find the maximum and minimum, and then think about how we can use the maximums and minimums to answer questions like this. Applications. If we want to find the maximum height of a ball that's in the air, or the maximum sales based on a quadratic equation, can we determine the maximum, not sales, but profit for a company in a particular day, and can we find the maximum height of a ball when it's being thrown in the air based on that equation? Again, please try those on your own, and I will have solutions for you in the next video. Thanks for watching.